A submarine communications cable is a cable laid on the seabed between land-based stations to carry telecommunication signals across stretches of ocean. The first submarine communications cables, laid in the 1850s, carried telegraphy traffic. Subsequent generations of cables carried telephone traffic, then data communications traffic. Modern cables use optical fiber technology to carry digital data, which includes telephone, internet and private data traffic. Modern cables are typically about 25 mm in diameter and weigh around 1.4 kg per meter for the deep-sea sections, which comprise the majority of the run, although larger and heavier cables are used for shallow water sections near shore. As of 2010, submarine cables link all the world's continents except Antarctica. Early history: telegraph and coaxial cables. Trials after William Cooke and Charles Wheatstone had introduced their working telegraph in 1839. The idea of a submarine line across the Atlantic Ocean began to be thought of as a possible triumph of the future. Samuel Morse proclaimed his faith in it as early as 1840, and in 1842, he submerged a wire, insulated with tarred hemp and India rubber, in the water of New York Harbor, and telegraphed through it. The following autumn, Wheatstone performed a similar experiment in Swansea Bay. A good insulator to cover the wire and prevent the electric current from leaking into the water was necessary for the success of a long submarine line. India rubber had been tried by Moritz von Jacobi, the Prussian electrical engineer, as far back as the early 19th century. Another insulating gum which could be melted by heat and readily applied to wire made its appearance in 1842. Gutta percha, the adhesive juice of the Palaquium gutta tree, was introduced to Europe by William Montgomery, a Scottish surgeon in the service of the British East India Company. 20 years earlier, he had seen whips made of it in Singapore, and he believed that it would be useful in the fabrication of surgical apparatuses. Michael Faraday and Wheatstone soon discovered the merits of gutta percha as an insulator, and in 1845, the latter suggested that it should be employed to cover the wire which was proposed to be laid from Dover to Calais. It was tried on a wire laid across the Rhine between Deutz and Cologne. In 1849, C.V. Walker, electrician to the Southeastern Railway, submerged a 2-mile wire coated with gutta percha off the coast from Folkestone, which was tested successfully. First commercial cables having earlier obtained a concession from the French government. In August 1850, John Watkins Brett's Anglo-French Telegraph Company laid the first line across the English Channel, using the converted tug Goliath. It was simply a copper wire coated with gutta percha, without any other protection, and was not successful. The experiment served to secure renewal of the concession, and in September 1851, a protected core, or true cable was laid by the reconstituted Submarine Telegraph Company from a government hull, the Blazer, which was towed across the channel. In 1853, further successful cables were laid, linking Great Britain with Ireland, Belgium and the Netherlands, and crossing the belts in Denmark. The British and Irish Magnetic Telegraph Company completed the first successful Irish link on May 23 between Portpatrick and Donaghadee using the collier William Hutt. The same ship was used for the link from Dover to Ostend in Belgium, by the Submarine Telegraph Company. Meanwhile, the Electric and International Telegraph Company completed 2 cables across the North Sea, from Orfordness to Scheveningen, the Netherlands. They were laid by the Monarch, a paddle steamer which later became the first vessel with permanent cable-laying equipment. In 1858, the steamship Elba was used to lay a telegraph cable from Jersey to Guernsey, onto Alderney and then to Weymouth, the cable being completed successfully in September of that year. Problems soon developed, with 11 breaks occurring by 1860 due to storms, tidal and sand movements and wear on rocks. A report to the Institution of Civil Engineers in 1860 set out the problems to assist in future cable-laying operations. Transatlantic telegraph cable. The first attempt at laying a transatlantic telegraph cable was promoted by Cyrus Westfield, who persuaded British industrialists to fund and lay one in 1858. However, the technology of the day was not capable of supporting the project. It was plagued with problems from the outset, and was in operation for only a month. Subsequent attempts in 1865 and 1866 with the world's largest steamship, the SS Great Eastern, used a more advanced technology and produced the first successful transatlantic cable. The Great Eastern later went on to lay the first cable reaching to India from Aden, Yemen, in 1870. British dominance of early cable. From the 1850s until 1911, British submarine cable systems dominated the most important market, the North Atlantic Ocean. The British had both supply-side and demand-side advantages. In terms of supply, Britain had entrepreneurs willing to put forth enormous amounts of capital necessary to build, lay and maintain these cables. In terms of demand, Britain's vast colonial empire led to business for the cable companies, from news agencies, trading and shipping companies, and the British government. Many of Britain's colonies had significant populations of European settlers, making news about them of interest to the general public in the home country. British officials believed that depending on telegraph lines that passed through non-British territory posed a security risk, as lines could be cut and messages could be interrupted during wartime. They sought the creation of a worldwide network within the empire, which became known as the All Red Line, and conversely prepared strategies to quickly interrupt enemy communications. Britain's very first action after declaring war on Germany in World War I was to have the cable ship Alert cut the 5 cables linking Germany with France, Spain and the Azores, and through them, North America. Thereafter the only way Germany could communicate was by wireless, and that meant that Room 40 could listen in. The submarine cables were an economic boon to trading companies because owners of ships could communicate with captains when they reached their destination on the other side of the ocean, and even give directions as to where to go next to pick up more cargo based on reported pricing and supply information. The British government had obvious uses for the cables in maintaining administrative communications with governors throughout its empire, as well as in engaging other nations diplomatically and communicating with its military units in wartime. The geographic location of British territory was also an advantage, as it included both Ireland on the east side of the Atlantic Ocean and Newfoundland in North America on the west side, making for the shortest route across the ocean, which reduced costs significantly. A few facts put this dominance of the industry in perspective. In 1896, there were 30 cable-laying ships in the world, and 24 of them were owned by British companies. In 1892, British companies owned and operated 2/3 of the world's cables, and by 1923, their share was still 42.7%. During World War I, Britain's telegraph communications were almost completely uninterrupted, while it was able to quickly cut Germany's cables worldwide. Cable to India, Singapore, Far East and Australia. Throughout the 1860s and 70s, British cable expanded eastward, into the Mediterranean Sea and the Indian Ocean. An 1863 cable to Bombay, India, provided a crucial link to Saudi Arabia. In 1870, Bombay was linked to London via submarine cable in a combined operation by 4 cable companies, at the behest of the British government. In 1872, these 4 companies were combined to form the mammoth globe-spanning Eastern Telegraph Company, owned by John Pender. A spin-off from Eastern Telegraph Company was a second sister company, the Eastern Extension, China and Australasia Telegraph Company, commonly known simply as the Extension. Submarine cables across the Pacific. The first trans-Pacific cables were completed in 1902-3, linking the U.S. mainland to Hawaii in 1902 and Guam to the Philippines in 1903. Canada, Australia, New Zealand and Fiji were also linked in 1902 with the Trans-Pacific segment of the All-Red Line. 88 years later, the North Pacific Cable System was the first regenerative system to completely cross the Pacific from the U.S. mainland to Japan. The U.S. portion of NPC was manufactured in Portland, Oregon, from 1989 to 1991 at STC Submarine Systems, and later Alcatel Submarine Networks. The system was laid by Cable and Wireless Marine on the CS Cable venture in 1991. Construction transatlantic cables of the 19th century consisted of an outer layer of iron and later steel wire, wrapping India rubber, wrapping gutta percha, which surrounded a multi-stranded copper wire at the core. The portions closest to each shore landing had additional protective armor wires. Gutta percha, a natural polymer similar to rubber, had nearly ideal properties for insulating submarine cables, with the exception of a rather high dielectric constant which made cable capacitance high. Gutta percha was not replaced as a cable insulation until polyethylene was introduced in the 1930s. In the 1920s, the American military experimented with rubber-insulated cables as an alternative to gutta percha, since American interests controlled significant supplies of rubber but no gutta percha manufacturers. Bandwidth problems. Early long-distance submarine telegraph cables exhibited formidable electrical problems. Unlike modern cables, the technology of the 19th century did not allow for inline repeater amplifiers in the cable. Large voltages were used to attempt to overcome the electrical resistance of their tremendous length, but the cable's distributed capacitance and inductance combined to distort the telegraph pulses in the line, reducing the cable's bandwidth, severely limiting the data rate for telegraph operation to 10 to 12 words per minute. As early as 1823, Francis Ronalds had observed that electric signals were retarded in passing through an insulated wire or core laid underground, and the same effect was noticed by Latimer Clark on cores immersed in water, and particularly on the lengthy cable between England and The Hague. Michael Faraday showed that the effect was caused by capacitance between the wire and the earth surrounding it. Faraday had noticed that when a wire is charged from a battery, the electric charge in the wire induces an opposite charge in the water as it travels along. In 1831, Faraday described this effect in what is now referred to as Faraday's law of induction. As the two charges attract each other, the exciting charge is retarded. The core acts as a capacitor distributed along the length of the cable which, coupled with the resistance and inductance of the cable, limits the speed at which a signal travels through the conductor of the cable. Early cable designs failed to analyze these effects correctly. Famously, E.O.W. Whitehouse had dismissed the problems and insisted that a transatlantic cable was feasible. When he subsequently became electrician of the Atlantic Telegraph Company, he became involved in a public dispute with William Thomson. Whitehouse believed that, with enough voltage, any cable could be driven. Because of the excessive voltages recommended by Whitehouse, Cyrus Westfield's first transatlantic cable never worked reliably, and eventually short-circuited to the ocean when Whitehouse increased the voltage beyond the cable design limit. Thomson designed a complex electric field generator that minimized current by resonating the cable, and a sensitive light beam mirror galvanometer for detecting the faint telegraph signals. Thomson became wealthy on the royalties of these, and several related inventions. Thomson was elevated to Lord Kelvin for his contributions in this area, chiefly an accurate mathematical model of the cable, which permitted design of the equipment for accurate telegraphy. The effects of atmospheric electricity and the geomagnetic field on submarine cables also motivated many of the early polar expeditions. Thomson had produced a mathematical analysis of propagation of electrical signals into telegraph cables based on the capacitance and resistance. But since long submarine cables operated at slow rates, he did not include the effects of inductance. By the 1890s, Oliver Heaviside had produced the modern general form of the telegrapher's equations, which included the effects of inductance and which were essential to extending the theory of transmission lines to higher frequencies required for high-speed data and voice. Transatlantic telephony. While laying a transatlantic telephone cable was seriously considered from the 1920s, the technology required for economically feasible telecommunications was not developed until the 1940s. A first attempt to lay a pupinized telephone cable failed in the early 1930s due to the Great Depression. In 1942, Siemens Brothers of New Charlton, London, in conjunction with the United Kingdom National Physical Laboratory, adapted submarine communications cable technology to create the world's first submarine oil pipeline in Operation Pluto during World War II. TAT-1 was the first transatlantic telephone cable system. Between 1955 and 1956, cable was laid between Gallanic Bay, near Oban, Scotland, and Clarenville, Newfoundland and Labrador. It was inaugurated on September 25, 1956, initially carrying 36 telephone channels. In the 1960s, transoceanic cables were coaxial cables that transmitted frequency multiplexed voiceband signals. A high-voltage direct current on the inner conductor powered repeaters. The first-generation repeaters remain among the most reliable vacuum tube amplifiers ever designed. Later ones were transistorized. Many of these cables are still usable, but have been abandoned because their capacity is too small to be commercially viable. Some have been used as scientific instruments to measure earthquake waves and other geomagnetic events.